So exam 2. We have saturated liquid water in a piston cylinder, and it starts with a volume. So the process goes from state 1 to state 2. At state 1, it's a saturated mix. And at state 2, nope, that's wrong. It's liquid at state 1. And it's a mix at state 2. The volume starts at, so since it's liquid water at the start and we're given the specific volume for a saturated liquid and a saturated vapor, we know that the specific volume at state 1 is 0.001. And we don't know what this is. So we're trying to figure out the quality of this. Well, the first thing we can do is, since we know that the volume at state 1 is equal to the mass times the specific volume at state 1, we have that 0.1, the total volume that's given, is equal to the mass times the specific volume. And so the mass is equal to 100 kilograms. At state 2, we know that the actual volume is 10. Over here, we knew that the actual volume was 0.1. And so now we can use what we know about the mass to say that 10, since it's the same material, no material's gone anywhere, we know we can say 10 is equal to 100 times the specific volume at 2. And so the specific volume at 2 is equal to 0.1. Now we can use the quality equation. So quality says for any property, the actual specific volume is equal to X times the specific volume in the gas form plus 1 minus X times the specific volume in the liquid form. And so we get that 0.1 is equal to X times, this is all stuff that's given now, 1.694 plus 1 minus X times the specific volume in the liquid form, which we're just using 0.001. And from this, you can get that the quality is equal to about 0.058. Okay, so 5.8% of this stuff in state 2 is a vapor, and the rest is liquid. Any questions about that? And then the second part is, it's still using the same values, but it's somewhat unrelated to the first part. We're trying to figure out the work of expansion. So we're going to use this equation. It says that this is a constant pressure process. So we can pull the pressure out. The pressure is 1 bar. I'm going to put everything in SI units. I didn't take off points for this, but you need to show units on your answers. So switching to SI units is a good way to go. But if you don't switch to SI units, you have to keep track of it. So 1 bar is 1 times 10 to the 5th times the integral from the starting volume of 0.1 to the finishing volume of 10 dV. And you get that the work of expansion is 0.99 times 10 to the 6th joules, about 1 megajoule. Look at the changes in volume here. This is just for like intuitive understanding. This is a good thing to notice. Like, look at how big that change is in volume. It only took converting 6% of that water to steam to have a 100-time increase in the volume. It's a huge volume increase, over 1,000 times that you get from converting all the liquid to vapor. Any questions about number 1? Okay, number 2. So you have an ideal gas. And you have 5 kilograms of it. At state 1, you have a pressure of 10 bar. And a temperature of 370 Kelvin. And it expands to a final state where the pressure is 5 bar, so 5 times 10 to the 5th pascals. It's an isothermal process, so the temperature stays the same. And it's internally reversible. And this gas has an R value of 300. In SI units. Okay, so the first thing we're going to do is calculate the change in specific entropy. You have an equation for that for an ideal gas. So the change in specific entropy is equal to Cp times the natural log of 370K divided by 370K minus 300 times the natural log of the pressure at state 2 divided by the pressure at state 1. We don't know Cp, but the natural log of 1 is 0, so this goes away. And so you get that the change in specific entropy is negative 300 times the natural log of 0.5. And you get about 207.9 joules per kilogram Kelvin. Now for the second part, we have the change in specific entropy. We want to calculate the total heat transfer. Well, the first thing you have to recognize is, okay, so this is internally reversible, which means that the change in entropy is equal to the heat transfer divided by the temperature. Okay, that's only true if the process is internally reversible. So that's why you were given that information. What we figured out here was the specific entropy. So 207.9. Well, let me write it like this. The change in extensive entropy is equal to the mass of 5 kilograms times the change in the specific entropy, so that's 5 times 207.9. So that is 1039.72 joules per Kelvin. The temperature is constant, so 1039.72 is equal to the total heat transfer divided by the Kelvin temperature of 370 Kelvin. And so the heat transfer is 0.39 about times 10 to the 6th joules. Is that heat coming into the system or leaving the system? Into, yep. So that's using the sign convention that we started with the first law. Anyone have any questions about any of that? So what were you, okay, so you had to use the expression for change in specific entropy for an ideal gas. You had to recognize that even though you didn't know Cp, that first term is going to be 0, so it doesn't matter. Then you had to recognize that the change in specific entropy is not the same thing as the change in extensive entropy, and that for the relationship between heat and temperature, you needed the actual entropy, not the specific. And then the last one, you have a 1 kilogram metal part that starts at 1,000 Kelvin. You have a mass of the metal of 1 kilogram. So all this is at state 1. You have a temperature of the liquid water of 280 Kelvin and a mass of the liquid water of 30 kilograms. And for part A, and it gives you the specific heats. C for the metal is 0.46 times 10 to the third joules per kilogram Kelvin. Specific heat for the water is 4186 joules per kilogram Kelvin. And we want to first show what the equilibrium temperature is. So for that, we're going to use the fact that this, what does it say? It's an insulated tank. So there's not going to be any heat exchanged with the surroundings. These are both incompressible. And for incompressible, we know that C is equal to du d temperature. So du for the metal is equal to, this 0.46 times 10 to the third is 460. So this is equal to 460 dt for the metal. You can integrate both sides and you get that the change in specific internal energy for the metal is equal to 460 times the change in temperature, which is the equilibrium temperature minus the starting temperature. We're going to get all our temperatures in Kelvin. And thinking the same way, we can get the change in specific internal energy for the water is equal to 4186 times the quantity equilibrium temperature minus the starting temperature for the water. And now, since this is insulated, we know that adding up the two changes in extensive internal energy has to add up to 0. This is not the extensive one, you know. The change in actual internal energy for the metal is the mass of the metal times the change in specific internal energy for the metal. Same thing here. Okay. And so now we had 1 kilogram of metal. So 1 kilogram of metal times the specific heat for the metal, 460, times T equilibrium minus 1000, plus the mass of the water times its specific heat times the quantity T equilibrium minus its starting temperature is equal to 0. And so that equilibrium temperature comes out to be about 282.6 Kelvin. So 2.6 degrees higher than the water started. And then for step 2, we have to show that this is the final temperature, not the starting temperature. So we're going to do that. Since this is insulated, we can show that for this process, the total entropy of these materials is greater than 0 in the direction we're trying to show, and that it's less than 0 in the opposite direction. So we're going to use the fact that for an incompressible material, delta S is equal to specific heat times the natural log of the later temperature divided by the earlier temperature. And we're going to show that the change in total entropy is equal to the mass of the metal times the change in specific entropy of the metal plus the mass of the water times the change in specific entropy of the water, and that's greater than or equal to 0. Because in an isolated system, entropy can only increase. So we got 1 kilogram times the specific heat of the metal times the natural log of the later temperature divided by the earlier temperature plus the mass of the water times its specific heat times the natural log of the final temperature of the water divided by its starting temperature. And you get a value of about 590 joules per Kelvin. What if your assumption was that it's going to go the other direction, start at 282.6 and then go back to 1,000 and 280? In both of those two terms, the fractions inside the log would switch. And so that has the effect of making the whole thing negative. So let's say whereas 1 times 460 times the natural log of 1,000 over 282.6 plus 30 times 4186 times the natural log of 280 over 282.6 is equal to negative 590 joules per Kelvin. And that's impossible. Any questions on that one? Overall, any questions on the exam? Okay. So last time we started talking about the Rankine power cycle. And for each stage, for each process, we started with the first law for control volumes. And canceled everything except W dot over M dot or Q dot over M dot. And HI and H exit. Okay. The work was the one that we kept for the turbine. And the pump. And the heat is what we kept for the boiler and the condenser. So I want you to notice that since this is, we went through the whole process when we did it, but since this is kind of like the simple, take-home message of the whole thing, this makes it really easy for you to just figure out, even in your head, what the equation is for each of those stages. For the pump, W dot P over M dot is equal to negative W dot over M dot for the control volume in the equation. Just because of the sign of what we mean by W dot for the pump compared to the first law sign convention. Are you with me on that? So in the first law, W dot is positive if work is being done by the system, but the pump needs to bring in work. So that's why you get that negative. That's also the same. So that's true for one of the two cases with the heat. Which one do we have to switch the sign of Q dot? The condenser or the boiler?
Condenser?
Yep, that's right. So for the condenser, W dot over M dot is, nope, Q. Q dot over M dot is equal to negative Q dot for the control volume over M dot. This makes it easy to determine the final equation for each stage. Okay, so what's the equation for W dot for the pump over M dot? And second, let's do what's the equation for the heat at the boiler dot divided by m dot. Well, first let's think about so I'm going to represent the whole cycle on a temperature entropy diagram. There's state 1, state 2, state 3, state 4, and these are the stages. The turbine is from 1 to 2. The condenser is from 2 to 3. The pump is from 3 to 4. And the boiler is from 4 to 1. The first one we're trying to figure out is the expression for W dot over M dot at the pump. So we have that 0 is equal to Q dot minus W dot for the control volume plus M dot times HI minus HE. Okay, that's kind of the starting point once we're assuming that there's no heat transfer. No, what am I doing? What did I say? Yeah, the pump. So there's no heat transfer. Everything cancels except the enthalpies and either the work or the heat. So we get W dot for the control volume over M dot is equal to HI minus HE. For the pump, we know that the sign is switched, so we can say W dot for the pump over M dot is equal to HE minus HI. That's the effect of switching those signs. And since the pump goes from 3 to 4, we have W dot over M dot is equal to H4 minus H3. Okay, so like when I did that the first time in class, it took a full page or whatever, like a lot, but it doesn't take very much to think through this. There's only a couple of signs you have to picture in your head, like what's the starting sign of the work or the heat? You know, separate that out from enthalpy, and then you switch the enthalpies or not based on switch the order of the enthalpies or not based on whether the work or heat keeps the same sign or switches sign. So the second one, now we're doing this at the boiler. So we're going to start with the equation that says 0 is equal to Q dot CV plus M dot times the quantity H inlet minus H exit. So Q dot for the control volume over M dot is equal to, since I have to get this over on the other side, I have to switch the order of these, HE minus HI. You know, that's the negative of getting that over to the other side. Now for the boiler, the heat has the same sign as Q dot CV. So we have Q dot at the boiler divided by M dot is equal to, so the boiler, the inlet is 4, the exit is 1. So we have H1 minus H4. Any questions about that? All right, well, let's do a kind of typical example. I guess before I do that, let me tell you one more thing. Yeah, I don't think I'm going to have the time to get through this whole example. So let me do something, tell you another kind of thing first, and then we'll do both examples next time. Okay, so let's say one more detail, and this is about how the condenser works. So okay, we know that the working fluid, the refrigerant, or I guess this is a power cycle, the water that is flowing through the tubes gets to the condenser, and you can see on this temperature entropy diagram that in the condenser, it goes from, what's the phase at state 2 when it enters the condenser? That's a mix, right? So it's a vapor liquid mix, and it finishes the condenser as a saturated liquid. Okay, so this fluid comes in at state 2. And goes through here, it comes out at state 3. And this is a saturated mix. This is a saturated liquid. How does it make that happen? It does it by passing a cooling liquid, through a mesh network that's thermally in contact with this liquid, going the other direction, like this. Okay, so this is the cooling water. And the only heat transfer from the working fluid is to the cooling water. So to do any calculations that deal with the cooling water, like if you're trying to figure out starting or a final temperature of the cooling water, to do any calculations involving that cooling water, treat the entire condenser as a control volume. So that includes, that includes the inlet and exit of the working fluid and the inlet and exit of the cooling water. So including the inlet and exit of the working fluid and the cooling water. And since that cooling water is a liquid the whole time, treat the cooling water as incompressible. And also treat it as constant pressure. So incompressible and isobaric, which means constant pressure. And then use the first law for control volumes. So for example, let's say that you have, how long is this going to take? Oh yeah, we can definitely do this. Okay, so let's say that you have working fluid enters a steady state condenser. At a quality of 0.6, a pressure of 0.2 bar, and a mass flow rate of 4 kilograms per second. Let's say that the cooling water has a mass flow rate of 20 kilograms per second and enters at 10 degrees Celsius. What's the exit temperature of the cooling water? Well, I'm going to start with this whole big ugly thing, and then we'll cross stuff out. So we're using the first law for control volumes. dE dt is equal to Q dot for the control volume minus W dot for the control volume plus the mass flow rate. Okay, well, it is going to be steady state. So I'm going to treat the mass flow rate at the inlet for the cooling water as just the overall mass flow rate for the cooling water. Same with the working fluid. So just so we don't have like a million subscripts. So first we have m dot for the working fluid. Hold on. Okay, M dot for the working fluid times the quantity so for the working fluid, the inlet is state 2. I'm going to leave off the potential and kinetic, I guess, for now, just right at the start, minus the mass flow rate for the working fluid times the specific enthalpy at the exit, which is H3. That's not all that's coming in and leaving for the condenser. We also have that cooling water, so plus M dot for the cooling water times the enthalpy at the, I'll call this the inlet, so H sub I is referring to the cooling water, minus M dot for the cooling water times the enthalpy at the exit. And then the other stuff that goes away because it's steady state, I guess, is just this. What work is done? Is there any work of expansion? No. These are rigid pipes, so this goes away. Is there any heat transfer? This is one to pay attention to because the whole thing is about heat transfer. But if you think about what we've drawn our box around, it's all heat transfer from one thing in the system to another thing in the system. And so this goes away too. Okay, so this goes away because the only heat transfer is to another thing in our system. All right, so now what do we have? We have, we could write it as M dot for the working fluid times the quantity H3 minus H2 is equal to M dot for the cooling water times the quantity H inlet minus H exit. And now we're given everything we need in order to calculate. We can get both of these from the table. So at a pressure of, remember we know that the working fluid going through the condenser is at constant pressure. And so we have a pressure for the working fluid of 0.2 bar. We know that let's see where it enters. So we know that H gas, that's something you can look up, is 2609.7 times 10 to the third. That would be joules per kilogram. We know that H for the liquid is 251.4 times 10 to the third joules per kilogram. And so since we know the quality, we can figure out that the specific enthalpy coming in. So that is at state 2 is 0.6 times 2609.7 times 10 to the third plus 0.4 times 251.4 times 10 to the third. And so that is equal to 1666 times 10 to the third, the devil's enthalpy. Coming out of the condenser, it's a saturated liquid. So H3 is just 251.4 times 10 to the third. And now what can we figure out about the enthalpy for the cooling water? Well, we're assuming that that's incompressible, and that gives us a lot of ability to calculate stuff. So for incompressible, at a constant pressure, we know that specific enthalpy is equal to specific internal energy, or let's think of it this way. The change in specific enthalpy is equal to the change in specific internal energy plus the change in pressure times volume. Well, what's delta PV if you have constant pressure and it's incompressible?
Work over...
Yeah, it's incompressible means V is constant. Constant pressure means P is constant. So this just goes away. Okay. And so the change in specific enthalpy is just equal to the specific heat. You know, so now specific change in specific enthalpy is just equal to the change in specific internal energy. So this is just equal to C change in temperature. Well, we can use this equation to figure out, so if I call this equation 1, we know that the specific heat of water is 4186. We know the change in temperature is the final temperature minus the initial temperature that they gave us. Where is that? 20 degrees Celsius. And so we can write that, what? Oh, yeah. So equation 1 says the mass flow rate of the working fluid, what was that? 4 times H3 minus H2, which is 1666, less than a minute left, minus 251.4 times 10 to the third is equal to the mass flow rate of the cooling water, 20, times the change in enthalpy, so 4186, times the quantity T minus 10. Now you only have one variable. Yep. Do the algebra, and the temperature at the exit is 77.6 degrees Celsius. Okay, any questions about that? All right, that's all.